Bismillahirrahmanirrahim. Respected teachers, dear colleagues, and dearest students, Assalamualaikum. Before I start the presentation, I would like to thank our worthy director, Dr. Lakshman, for his motivation to present this seminar on my research area. So the topic of my seminar is self-organization in complex networks, network analysis, escaping networks, and beyond. So I will cover these three topics, and then we shall see what are the things which we can cover from after these terms. So this one is the outline of my presentation. I will start with motivation. Then I will give you introduction to complex networks. That's very important. Then I will discuss network analysis methods. Again, these are basic things which we need to know for better understanding of the topic self-organization and description networks. Then I will give you introduction of, about the birth of network science, where from it started and now where it has reached. Then I will discuss briefly few models which are very important to understand this topic, and then I will describe my research problem. Then I will also show you a few results of modeling analysis which I have done in my PhD, and then we shall discuss future work and direction. So I start with the motivation. One of the most prominent physicists and mathematician, an Italian physicist, Galileo Galilei said, measure what is measurable and make measurable what is not so. So in this world, many quantities and many phenomena have been measured, but still there are many phenomena which have not been yet measured, and they are very difficult to measure. So we shall see what is difficult in measuring certain phenomena. Also, religious scholar or the founder of Buddhism religion, Buddha said, a net is made up of a series of tiles. So everything in this world is connected by a series of tiles. Tile means a link. If anyone thinks that the mesh of a net is an independent, isolated thing, he is mistaken. It is called a net because it is made up of a series of interconnected meshes, and each mesh has its place and responsibility in relation to other meshes. So very long ago, the religious scholar even he realized the importance of networks. So networks are everywhere. We cannot underestimate the importance of networks. Now, I will start the presentation with simple definitions which are very important, and whole presentation is depending on these definitions. So it's very important to understand. Simply, a network is composed of two things, namely nodes and links, where the nodes characterize the components which constitute the network, and links express the relation or connectivity pattern between the nodes. So this is simple definition. All of you are from IT, software and telecom, so you know the basic definition of network. Now again, another important definition is about complex system. The commonly accepted definition of complex system is a system consisting of many interacting units whose collective behavior cannot be explained from the behavior of the individual units alone, according to Gonzalez. Then third definition, based on both these definitions, is a complex network is a network with non-trivial topological features, with patterns of connection between their elements that are neither purely regular nor purely random. So up till now, I think all of you know the topologies in computer networks. We know the ring topology, mesh, star, bus, hybrid. But beyond these topologies, there are many others which we can find in real-world networks, real-world system. So there are many different complex systems in the world which can be represented as complex networks. Therefore, from the last decade in the field of complex systems, researchers have been trying to model and analyze very large complex systems as networks to get more comprehensive findings about their internal working mechanism and overall behavior. Now, it has become possible, the analysis and modeling has become possible due to the availability of huge amount of data with the tremendous storage capacity of modern computers, and the high processing speed has permitted analysis on that data on a scale far larger than previously possible. This is the reason network modeling and analysis have become very effective way of understanding these complex systems in many diverse fields of life such as sociology, transportation, technology, disease spreading, security, biology, ecology, finance, and many more. So both these books are, both these authors have written very important book. If someone is interested, they can read. For example, now I need to give some examples. What are the real world networks and how many researchers have worked on the basis of real world networks. For example, in the category of technological networks, the World Wide Web, electric power grid, internet, and routers connectivity all are complex networks. Similarly, in social systems, the examples include human sexual context networks, network of friendships, and covert or terrorist networks, which are also known as dark networks. Further, in transportation systems, the examples are air transportation network, railways networks, and highways networks. Even in ecological systems, the examples are networks of species. Moreover, the biological and disease networks include gene regulatory networks, protein-protein interaction networks, dengue as epidemic disease network, and many more. Hence, we can deduce that the networks are all around us. As these systems are very large and complex, it is difficult to understand these complex systems just by only examining the individual or separate components alone. Therefore, modeling the way these components are interconnected in a system is very important for deeper understanding of the system as a whole. Further, despite the enormous variation in their components, function, and sizes, these networks are surprisingly similar in topology, leading to the conjecture that complex systems are governed by the ubiquitous self-organizing principle. Now, I will discuss what is self-organization later on. We have different networks, but they have different components. The features are different. The components features are different. They have different functions. They have different sizes. But ultimately, the researcher have found they are following a ubiquitous self-organizing principle. And what is that? We shall know later on. So, a network actually consists of a set of n nodes and a set of l links, where n is the size of network. So, thus, a graph is a mathematical abstraction of a network, and in network, the nodes and links can represent different elements, and their interaction depends on the network under modeling and analysis. So, this is one simple example of network where we have 9 nodes and we have 9 links. So, these are the nodes and these are links. Very simple representation by using graph. So, from this viewpoint, each element is represented by a site in physics. In physics, we say site. In computer science, we say node. In sociology, we say actor. In graph theory, we say vertex. And interaction between two elements correspond to a bond in physics, link in computer science, tie in sociology, or age in graph theory. Now, I want to show you some examples of complex networks, with how much they are complex. So, just by only visualization, we cannot find their behavior, how they behave, how collectively they behave. So, we need to perform some network analysis on these systems. So, this one is the network of internet backbone, where routers are the nodes and physical lines are the links. So, I have taken this from Mark Burton's paper. Another internet net, where we can see thousands of routers are there and thousands of links are there. So, it's very difficult to analyze how this system collectively behaves. Similarly, I have taken another example from transportation network. So, this is the air transportation network of America. This is a map of America, where we can see these are the nodes, and nodes are representing the airports of America, and links are the direct flights. So, you can see huge nodes have huge number of links, where many they have a few links. So, here airports and links, airports are nodes and links are direct flight. Okay, this one is the New York State power grid, and we use power grid for transporting electricity. So, here nodes are power plants and transformer, etc., and links can be cable. Again, you can see this is very complex. Similarly, we have examples of biological networks, where we have neural networks, where neurons are the nodes and links are axons. Similarly, we have a protein-protein interaction network, where nodes are proteins and links are the interaction. Again, they are very complex to analyze and understand. Okay, now before going to analyze a particular system in the network, we need to know what type of networks are available. Okay, So there exists different classification of networks according to the direction of the links, whether the networks are directed or they are undirected, according to the kind of interaction, whether weighted or unweighted. So see here, this link has this link is thicker than this one, and this node is also thicker than this one. It means they have different weights. Then according to the differences between nodes, bipartite or not. So few networks can be represented through this bipartite graph, where we have two different sets of nodes, and they are, heterogeneous in nature. Then according to the evolution of their topology, whether the network is static or the network is evolving. Okay, now despite the different types of networks, which in turn are obtained from completely different interacting systems like people, neurons, proteins, routers, we can see that they share some universal properties. Now see, for example, just by only visualization, just only by visualizing this network, can you say, is it a social network, or a technological network, or a biological network, or a transportation network? Though this one is the gene regulatory network, which is a biological network, but just only by visualization you cannot say what type of network is this. I mean, have we ever thought how diseases are transmitted through social networks? How computer viruses spread through the internet rapidly? How rumors spread fast? So you can get the answer of all these questions if you know the topology of the system is a network. This is very important to find the topology. Now these are the research questions which I have answered in my thesis. What properties are appropriate for characterizing the topology and behavior of real world networks? In my case, I have worked on illegal immigrants, which I will discuss later on, and how these properties can be measured, how you will measure that a particular system has a particular topology. Then what is the relationship between an evolving network's local properties, its nodes and links in case of states and countries with illegal immigrants in Malaysia, and its emerging global structure and behavior, how globally and how locally the nodes are behaving. Which network analysis metrics are necessary and sufficient to identify the critical components of a network? Which method of projection is suitable for weighted two-node network of illegal immigrants? What are the vulnerabilities of this network to infiltration and or attack? Do these networks exhibit self-organization? So these are the questions which I answered in my thesis, and I will discuss later on. Okay, so to understand the answer of my question, we need to understand few basic things, which are very important. Otherwise, it will be very difficult for you to understand. So there are few network analysis metrics, though there are many, but I will just discuss few of them so that you can get an idea what are the network analysis metrics. So the first one is simply adjacency matrix. Adjacency matrix can be used as the simplest method of representing any type of network. For example, if there are n number of nodes in the network, and these are interconnected with some links m, where we assume that these links are undirected, then it is possible to identify the connection structure of the network by n into n matrix A. So here is a simple example. Say if we are not including the weight of a link here. So this is a simple network, and we can represent this simple binary network without including the weight of the link through this adjacency matrix. Say for example, node 1 is connected with 3, node 1 is connected with 2. So 1, 2, 3, 4, 1, 2, 3, 4. 1 is not connected with itself, so 0. 1 is connected with 2, it is 1. 1 is connected with 3, it is 1. 1 is not connected with 4, so it is 0. So this is a simple representation of a network. Similarly, we can have a weighted network where we can represent the weighted network through weighted matrix, and you can see here we can differentiate the links in terms of weight. So link 1 is connected with link 3, but the weight is 4.1. Link 1 is connected, node 1 is connected with node 2 with 2.3. So this is a simple representation of any network through adjacency matrix. Now all the diagonal elements of this matrix Aij are 0. It means the nodes in this network has no self loops, and this matrix is symmetric because there is a link between J and I, and also a link between I and J. So therefore, one can think of a number of extensions to represent more complicated types of networks through adjacency matrix. This is a very powerful tool in spite of its simplicity in analyzing the networks, as a lot of information is encoded into it. Then we have another Meyer, which is very important to understand, otherwise we will not understand what is scale free. So that is node degree and strength, which are local Meyers. The node degree is the number of links directly connecting to the node with other nodes in the network. So the degree ki of the node I can be computed as given in equation 1. So we can have an adjacency matrix and we can find the total number of links with particular node, where ki represents the degree of node I, and A is the adjacency matrix, and the entry Aij represent connectivity if the value is 1, otherwise it is 0, and N is the total number of nodes in the network. Okay, so that was simple degree where we were not counting the weight of the links. So based on the weight of the links, we have weighted degree or strength of a node. So in weighted networks, the weighted degree or strength can be defined as the sum of a node direct links weight is given in the equation. So this is the strength of the nodes, where W represents the weighted adjacency matrix. The value of the entry Wij in matrix is greater than 0 if the node I is connected with J, whereas the value show the weight only. Now, so this is a simple example. If I want to find what is the degree of C, so it is degree 2. But if I want to find what is the strength of this node, then we can say it is 12. 6 plus 6, 12. So similarly, we can have different nodes with different degree and weight. Now, what is node degree centrality? Because in network analysis, it's very important to find the critical links and nodes where we need to focus. So for that we use many different Meyers, but node degree centrality is very simple Meyer so that you all people can understand. So the identification of main or critical nodes in complex networks analysis has remained very important topic for the researchers, because if a node is more central as compared to others in a network, it has three main advantages. Number one, placement or location can potentially control the traffic flow among other nodes. Number two, it can have more direct links. Number three, from that node, one can reach to all other nodes very quickly. Further, as node strength do not consider the number of links with particular node, therefore it gives only rough idea for the node's actual contribution and involvement in the whole network from degree centrality point of view. See the example here. If we see, the weight of this node E is 12, and the weight of the A node is again 12. So here it is only 3, degree is 3, and the node A has degree 4. So though both these nodes have same strength, but this one is not important. So A is more important. Why? Because it has 4 links as compared to 3. So to quantify this, Opsahl et al. Has proposed a very realistic approach for degree centrality in vector networks by considering both the number of links and the total weight of links, which we say strength. So here this one is weighted degree centrality, and alpha is the tuning parameter. So you can see it's very simple. If we take value of alpha as a 0, so you will get only degree, because strength divided by degree power 0 will be 1, so you will get degree. If I am taking alpha as a 1, then degree will be cancelled and you will get a strength. But what I want to see, the involvement of both the weight and the degree, then you have to set this alpha tuning parameter 0.5, and then you will get the actual involvement of degree as well as the strength. So where alpha in this equation, the loss equation which I have shown, works as tuning parameter. If the value of alpha is 0, then it will only focus on the number of links connected with nodes, and if the value is 1, then it will include the weight of the links only. If the value of alpha is in the range of 0 and 1, then it will measure both the weights and degree favorably. Now second term is how we can compute the shortest path in network. I am just explaining because they are important. If you will not understand degree, shortest path, strength, then you will not understand the term skill free. So the shortest routes or paths in unweighted network depends only on the number of intermediary nodes from source node to destination node, as we have used RIP, routing information protocol, where we see how many hop count are there in between source and destination. So it's very simple to compute in case of unweighted network. The length of the path is defined as the minimum number of links connecting the node, connecting the two nodes in the network either directly or indirectly. So the shortest or geodesic route between nodes I and J can be defined formally as given in equation 1. So just we need to see how many hop counts are there, how many intermediary nodes are there, where D, I, J is the distance between nodes I and J, and H are the nodes that come in between root of nodes I and J. Now, it was all about the binary routes where we do not have the weight of links. When links are weighted, then simple or binary routes are not important because links can be differentiated and links with high valued weight would be preferred as compared to low valued weights. For example, flow of data from one router to another router can be sent via high bandwidth link as compared to low bandwidth links more efficiently and faster. Therefore, if the links weight represent the strength, then the paths which are based on strong links become shorter as compared to weak links. For example, the network as shown in figure on next slide has three routes between nodes D and E, and all these routes have different weights and intermediate nodes. So see here, though we can reach from E to D through this route, but it is low weight, whereas this is the longest route, but again it is high weight. When the links in network represent the diffusion of resources, information, diseases, etc., then the paths and the speed clearly affected by the weight of links. So, many attempts have been made to find shortest path in case of weighted network as given in this author's paper. And all of you are very much familiar with the Dijkstra shortest path algorithm, most of you have used. So, Dijkstra long ago proposed the algorithm which remained very popular for finding all shortest paths in network. Therefore, in weighted networks, links weight need to be inverted before applying the Dijkstra algorithm for the identification of shortest routes as proposed by Brandeis and Newman. Because in case of Dijkstra, if we apply directly the Dijkstra algorithm for finding shortest path, you will see this will be considered as a cost. So this will be the longest route according to the Dijkstra algorithm, and this will be the shortest. But in case of real world networks, this is not the shortest route because it has only weight 1. So, and this is highest weight. So this will be the most feasible path. So therefore we need to invert the weight so that we can have better paths. So in this way, the resultant links weight can be considered as cost, and hence weak links have greater value and strong or cheap links have low values. Therefore, links with higher weight become stronger and it takes less paths to transfer information through that link. The Newman and Brandeis proposed implementation of Dijkstra's algorithm can be formally defined as given in equation 1. This is a weighted distance. What we have to do, just we will invert the weight of the link. Now, here only we are considering on the weight of the links. We are not considering the number of intermediate routes as well. So, the Upsahal et al. Generalization used the tuning parameter alpha to transform the inverted weights before using Dijkstra algorithm to find the least costly path as given in equation. So, here alpha is the tuning parameter, which will, when we shall set the value of alpha is 0.5, so definitely it will include both the number of intermediate routes and also the weight of the links. It ensures that both the number of intermediary nodes and weight of the links contribute in identifying the shortest paths in weighted networks. Now, we have two other methods which are being used for identifying the important nodes in the network, and these are betweenness and closeness centrality in weighted complex networks. And both these are global measures because they are not focusing on the local nodes like degree and distance was focusing. So the betweenness centrality is again geodesic based measure that depends on the finding of shortest paths from node to node in the network. Therefore, it is a measure to quantify the importance of a node in the network on the basis of focal position on the shortest paths in between the remaining other pairs of nodes. So Freeman generalized the betweenness centrality by using this equation, where CV is the betweenness centrality of node I and GJK is the total number of shortest paths or routes in between two nodes, and GJKI is the number of those routes that passes through their node. So in our real world, even we have observed that few nodes works as a diffusing nodes. When you want to transfer information quickly to other nodes, just you need to send information to that particular node, and definitely it will diffuse information to majority of the nodes. So to quantify this measure, we need to find what betweenness. Now, whereas Upsahal generalization of betweenness centrality depends on their generalization of shortest routes, the betweenness centrality is formalized according to Upsahal as given in this equation. So again, this is a generalization where we are using the weight of the links as well, and by setting the tuning parameter alpha, we can control what we need, whether both or we need to just focus on the links or we have to just focus on the weight. Now similarly, we have another measure which is a global measure. It is closeness, and it is defined as the inverse of the sum of all shortest paths from main node to all other nodes in the network. Now free range formula is closeness is given in this equation. So closeness is the inverse of the farness. So by applying this method, we can find that how much a particular node is closer with other nodes in the network. So this is again a global measure, where CCI represents closeness centrality of node I in the network, and Dij is the distance between nodes I and J. Again, because we are not considering the weight of the links, so in 2010, Upsahal generalized closeness centrality, and it depends on the generalization of shortest paths. So closeness centrality has been formalized according to Upsahal as given in this equation, with alpha as a tuning parameter. Now the third and last one is transitivity and clustering coefficient. So it has been noticed and shown that many real world networks shows high degree of transitivity. Now this basic measure has received long ago the attention of researchers from theoretical and empirical research perspective of networks. For example, if node A is connected with node B and C, then there are chances that node B and node C are also connected with each other. So this is what a transitivity. Now from the network's topological point of view, it measures the presence of triangles in the network. Now to measure this transitivity, we use clustering coefficient. So clustering coefficient can be used to quantify this behavior of nodes in the network, and there are two versions of clustering coefficient to test this behavior. The first one is global. Global version is introduced to assess overall clustering behavior of network, and second is local clustering coefficient. It gives the indication of single nodes participation in the network. So I just do simple examples so that you people can understand what is the clustering coefficient and how it can be defined. So the global clustering coefficient is defined as the ratio of the number of closed triplets or triangles. Triangles means three nodes are connected over the number of total connected triplets, both closed and open. I mean three nodes with at least two links as given in this equation, where this global clustering coefficient GC represents the global clustering coefficient, and tau is the number of two paths, and tau delta is the number of these two paths that are closed by a triangle. So for the network shown in above figure, the binary global clustering coefficient, it means without considering link weight, we don't have weight over links. So this value will be 3 over 9 by 0.33. So how we have computed this? In this network, the closed triplets are H, GI, GHI, and GIH. And on the other hand, the open triplets are GH, GHJ, and GHK. Okay, so these are open triplets, so we can find the global clustering coefficient in this way. But binary global clustering coefficient without considering the weight of the links. Okay, now the weighted global clustering coefficient was proposed by Upsahal, where they define the triplet values based on 4 methods, namely the geometric mean, minimum, maximum, and arithmetic mean. Say for example, if we have a vector network and we have weight of the links, then how we can find the global clustering coefficient? We need to use 4 methods. The table shows the effect of using different methods to compute triplet value omega for closing these triplets, open triplets. So when we apply different methods, we can have different results. If we apply arithmetic mean, then we can have 0.41 for this network. If we apply geometric mean, we can have 0.43. If we apply minimum method, then we can have 0.37 like this. So therefore, it is very important to choose appropriate method based on the research question and data set for defining the values of triplet. So similarly, this one is the local clustering coefficient. I will not go into detail. And this is how we can find the density of the network. So this is also very important. We need to know what is the ratio between the actual number of links and total possible number of links in a network. So it is defined in one node network as a ratio in between the number of links available in network to all possible number of links in network as given in this equation. So number of possible links divided by total number of links, which we can find through this expression, n into n minus 1 over 2. So where nd is network density. Okay, so it was all about network analysis metrics. Though there are many network analysis metrics, and we can use different network analysis metrics for networks in different domains. Okay, it is not compulsory that we can use only these. But because I want to give you an idea that after finding a topology, the scale free, what will be effect on these special measures which I have discussed. Now, it's very important to give you an idea that how network science came into existence. So I'm just starting from Euler. So Euler is known as the father of graph theory. Why he is known as father of graph theory? Because he was the first person who gave idea about the vertices and edges. So Now, uh, actually, he was the resident of Königsberg, which is the old name of St. Petersburg in Russia.
Is he the one who invented the circle?
No, no, no. But Fourier transform can be. I mean, there are many. No, he has written 886 books, and he was blind after 40 years. And one more important thing, he had 13 children. He had 13 children. 1 3. No, I'm just really, it's a fact. I read the history. I mean, he has written 886. It's not. I'm not sure because it's not written. Yeah, really, I was surprised how it is. Really, I mean, it was surprising. The author
Maybe he
said.
got a notification of a letter from his children.
Okay, so what was the problem? Problem was to solve. Can we visit? These are land areas. And these which was divided by the river Prigel. So the problem was that can we pass? Is it possible to cross the 7 bridges only once without crossing twice a bridge? So what he did, he conceived this thing in the form of vertices and edges, where he divided the land area into vertices. This A, this is A, this is C, and this is D, and this is B. So A, B, C, and D. So now we can reach A through C, through 3 links, 1, 2, and again from C we can end in this in D. So this was, he conceived this like edges and vertices. So what was the solution? He said A0 is number of nodes with odd degree. Now you are very much clear what is degree. Okay, direct links. So this is odd degree, 1, 2, and 3. This node has 3 links. So if N0 is greater than 2, no solution exists. If N0 is equal to 2, only one solution is starting from one of the odd nodes. If N0 less than 2, there are solutions starting from any node. So what was the result of this formalization? A solution path cannot exist on a graph that has more than 2 nodes with an odd number of links. But we have seen that all the nodes have 3 links. So it is odd degree. So Euler declared the existence of the path does not depend on our cleverness to find. Rather, it is a property of the graph. So graphs or networks have properties hidden in their construction that limit or enhance our ability to do things with them. So in 19th century, the advancement in the research field of graph theory continued by many mathematicians, including William Hamilton, Gustav Kirchhoff, Thomas Kirkman, and Arthur Cayley. But their research and development in graph theory was based on theoretical mathematical objects as compared to the problems related to the real world system. Historically, the social scientists realized very earlier in the beginning of 20th century the applications of network analysis and used sociogram as networks. So the first person who, as a sociologist and psychiatrist, carried the systematic study of social relations as network was Jacob Moreno. He systematically collected and analyzed the pattern of interaction in very small groups like schools, classrooms, and worker groups. By observing the structure of social interaction and by drawing on the paper as nodes and links, one can predict the future behavior of or functioning of the network. He called his network a sociogram, in which nodes were represented as people and links were created if they had some kind of acquaintances. In 1967, Stanley Milgram, a social psychologist at Harvard, was interested in learning how many acquaintances it would take to connect two randomly selected individuals from population. So he performed a simple experiment, an empirical study, in which a group of people from Nebraska and Kansas, they are state America, was asked to send a letter to an unknown person in Boston. So what was the basic rule of the experiment? People should forward the letter to a person that they consider closer to the target person. I have given you a letter, and you know, you don't know the destination to whom we have to send letter. But on the basis of guess, maybe Sir Raza knows this particular person, then I'm just sending you. And then Sir Raza, when see, I don't know the person, there are to them. Then you can send to substars like this. So what were the results of one experiment? 232 out of 296 later were reached the target. Only 64 letters reached the target, which passed from 2 to 10. So when he took average, the average path length was to 5.2 steps. So he said the world is very small, and this experiment is known as what? 6 degrees of separation. All the people in this world are only 6 degrees away from each other. So this is a small world effect. Yes, we can reach to 1. Then the quantitative analysis and research of social scientists helped in further development of mathematical techniques. Anatole Rappaport, a mathematical psychologist, argued that the frequency distribution of links related with nodes in the network plays very important role to measure properties of a network. With his collaborator R. Somnoff, he proposed random graph, which was simple model of network. His model then independently studied by Paul Erdos with his collaborator Alfred Renier. The ER model remained very popular from late 50s to late 90s, and modeling of almost all complex networks was based on random graph theory. Now, we have to understand what is random graph theory. And in my research, I have negated this theory in terms of illegal immigrants. I have proved that illegal immigrant phenomena, if we see as a network, this is not random. This is scale free. So I have also included in a complex network literature that the phenomena of illegal immigrant distribution is not a random. Though many authors, many researchers have proved different phenomena. So now we have to understand network models, and this is the last. I will start my research work. So first we need to know what are regular networks. It was assumed and believed for a long time that the real world system and the pattern of connection between the elements of this system could be represented by some regular networks, for example, lattice, grid, and circle networks, where we have equal number of neighbors of the nodes. Then in 1959, this is one of the most important models, which was used for 40 years, from 1959 to 1999. So two Hungarian mathematicians, Paul Erdos and Alfred Renier, introduced the concept of random graph theory in the classical mathematical graph theory. According to them, complex networks topology can be best described by random graph. For example, if we have a large number of nodes in a network, and if we connect each pair of nodes with some fixed probability, then ultimate outcome will be physical example of ER random graph. The model has one basis: connects the nodes randomly. So the model is defined as, in a graph G with n nodes, each of the possible n into n minus 1 over 2 links exists with a given probability P. We can construct a random graph G from n nodes by selecting the number of links depending on the probability and total number of links. As the main parameters here are the number of nodes and connection probability P, so the GNP model will be the combination of all graphs in which a graph with G links occurs with probability this. Here M is the total number of possible links in network of n vertices. The degree distribution of ER model follow binomial distribution, as each link occurs with a fixed and independent probability, and therefore we can have this expression. Now, if we have a huge number of nodes, then due to this binomial coefficient in this distribution, we have to approximate it, and let us suppose the mean degree of network is lambda n minus 1 into P. Now, if we take the limit n tend to infinity any number of nodes, by keep the average degree fixed, then above equation tends to a Poisson distribution. Now, in this model, the structure of graph generated totally depends on the value of probability P. If the value is low, there will be very few links between nodes. See, when probability is 0, no any node is connected. When probability is 0.1, few nodes are connected. As we will increase the probability, we can have many connections. The Poisson distribution implies that, in particular, the number of nodes with degree G decays very rapidly around the average degree, and therefore all nodes have nearly same degree. In this way, the network will be homogeneously connected with short path length and low clustering coefficient. This is very important slide. So please try to focus on this. Therefore, random graph theory predicts that it is extremely rare to find someone who deviates from the average by having significantly more or fewer links than the average person. Only before the 1.5 decades ago, due to advancement in data processing and storage capability of modern computers, researchers observed that many real-world complex networks are not completely random. Now, if you focus on this distribution, this is a binomial distribution. If we say we have on vertical axis we have a number of routers, and we have, on the horizontal axis we have a number of physical links. Then we can have bell-shaped curve distribution according to the random graph theory. Or if we can see, we have a number of people and we have a height of people. Again, if we shall plot this distribution, we can have a binomial or Poisson distribution. So up to 1999, it was assumed that all the complex systems in the world can be described by the random graph theory. So what happened in 1999? So physicist from Hungary, Albert Waheed, he is the founder of this term, scale free. So he was, his student Reka Albert was doing PhD under supervision, and they were analyzing the World Wide Web as a network. The web pages were considered as nodes, and the hyperlinks were considered as edges. So what he observed? So a scale-free network model by Barabasi and Albert in 1999. This is one of the most basic and widely accepted model of complex networks. According to this model, there are two ingredients for modeling of dynamic networks, because up to 1999 only we were focused on the static networks. But the real world networks are not static, they are growing, they are evolving. So we need to model this growing phenomena. So he said we have two ingredients to describe this model. The first one is growth. The network extends continuously. And second one is preferential link attachment. What is that? Links are not made randomly, but preferentially. So here we can see at time 0, all the nodes are disconnected, and I have just skipped T1, then I have used T2, so we can have some type of interconnectivity. But how this network is evolving, we need to see. Let's suppose this third node is coming in network. So with whom this node will try to connect? It depends on what the preferential attachment. And what is preferential attachment? Let's suppose it start with m dot nodes, and then add a node with m edges at every time step. But m, the number of edges must be less than the actual number of nodes. So there are 3, so it must be 2, not 3. Now what is preferential attachment? How this node will try to select where I have to connect, with whom, which node I have to connect. So it depends on the probability of the distribution of the degree of the particular node I. So it is what? The degree of node I divided by the degree of all the nodes which are present in this network. So if this distribution will be high as some other, the new node will try to connect with that node. So it says there, let's suppose I'm giving an example so that you can understand, maybe a bit mathematics. So in a social network, let's suppose I have 3 friends, and I have another other friend, he has 5 friends. So if new person is trying to join that particular network, then he will select a person which has many friends, like 5 friends. So this is what a preferential attachment. Okay. Now, Barabasi and Albert analyzed the network of World Wide Web and found that no degree of World Wide Web does not follow random graph connections. Rather, it is a scale-free graph, and its degree distribution follows power law distribution, not a Poisson distribution, not a random distribution, not a binomial distribution. So how we can understand what is power law distribution and what is the Poisson distribution? So in a random network, we can see, if we see, these are x-axis is number of links, y-axis is number of links, and x-axis is number of nodes. So we can have bell-shaped distribution where we are not deviating from average value. We have the starting point, we have the ending point. Like the age of people can be from 1 year to 100 years, or the speed of cars can be, let's suppose, 1 kilometer per hour to 300 km per hour. But here, when he analyzed the World Wide Web, he found that many of the websites have few links, hyperlinks, whereas there were few websites which had many links, thousands of millions of billions of links. So he formalized this as he said power law distribution is the main reason for this. So we can also understand this phenomena, like if we take an example of the US road network, where we can say we have these intersections, you can see the maximum degree is 5 or 6. This one is 3, this one is 2. If we take an example of US air transportation network, then you can clearly see that there are few hubs. There are few airports which have huge number of links, whereas majority of the nodes have few links. Are you getting me? Is it clear? So here, gamma is a scale-free parameter in the sense that it does not depend on a characteristic scale of the network. Whether when we have a preferential attachment in network, when it grows with the help of preferential attachment, you cannot measure the scale. Whether you will see at a 1,000 or 10,000 or million or 10 million, it will look like same. So this exponent gamma has been measured as well as confirmed in number of research studies to be within the range of -2 and -3. So this is what universality. Now how we say this one is universal? See here, after the term scale-free networks, the introduction of scale-free networks, many researchers, they have tried to see they applied this model on their data set, and then if we see the gamma, the power exponent, you can see 2.45, 2.38, 2.78. This is actually decreasing curve. This one. This is a linear scale. If we plot the data on the linear scale, we can have this long tail distribution, and when we plot this linear scale on a logarithmic scale, then we can find this decreasing curve, and this decreasing slope is what the gamma power exponent. And when they found this gamma exponent in different networks, they found that it is always in between 2 and 3, no matter what domain is. So because see here, World Wide Web is a technological network, Internet is a technological network, movie actor is a social network, co-author is a social network, sexual content is a social network, metabolic is a biological network, protein is a biological network. So citation is again a phone call. So the result was surprising, because all these networks from different domains, why the value of this power exponent gamma is in between range of -2 and -3. So this is what a universal phenomenon. Though they have different properties, but they have something common. Is it clear? So now after a Barabasi model, because it was only focusing on the degree of the node, but in real world system, degree of the node is not important. We have other things. Say for example, to include the concept of fitness of nodes in the growth process of networks, Bianconi and Barabasi proposed fitness-based skill-free network model. In this model, a fitness parameter eta I is assigned to each node, which remains same throughout the changes of time. In this way, at each time step, a new node j with the fitness nj, eta j is added to the system, where eta j is chosen from the distribution. Now, the fitness parameter depends on the domain of a network, and it reflects the different abilities for each node to compete in the networks for getting new links. In this way, each new node connects one of its m links to the nodes already present in the network, and the probability to connect to a node I is proportional to both the degree and fitness of node I. So mathematically, this is represented in equation like this: eta I into ki, because now the new node will try to connect with a node which has highest degree as well as highest fitness parameter. So this generalized preferential attachment assures that even a relatively young node with a few links can acquire links at high rate if it has a large fitness parameter, as fit gets better phenomena. The previous was rich get richer. Now this one is what? Fit get richer. So we can understand this as very good website can get many links as compared to old but not popular website. Or in case of scientific papers, better papers can have more citation as compared to old but less important paper. So this is how the actual network grows. So this one is a preferential attachment, and you can see at some time few nodes become the hub nodes in the network. Again, in both these models, they are focused on the fitness of the nodes and also the number of links. But in reality, again, not only the number of links and the fitness of the node is important, but also the strength is important. So to address the issue of variation of links weight with various intensity and growth of nodes, Barsamele and Vespermanni introduced a model. They use worldwide airport network data. So according to this model, growth, this one is the last model, then I will start my research work. So starting from initial nodes connected by links with assigned weight W0, a new node N is added at each time step. This new node is connected to N previously existing nodes, choosing preferentially node with large strength. not a degree, not a fitness, but the strength of the node. According to the probability distribution that is given in this equation. So we are using here what is strength of node. See this diagram. So this one is a node and this one is the strength. How many links it has? 1, 2, 3, 4, and these links have weight. So new node will try to connect with this node I because it has high strength as compared to other nodes. So now how this weight will be adjusted, because weight can also be changed when the network grows, not only the nodes but the weight. So the weight of each new link Ni is initially set to given a value W0. This is W0. The creation of this link will introduce variation of the traffic across the network as shown in figure. So we can formalize this one like Si the strength, which can be computed again actual value of strength plus weight of the new link, and then partial, which is the dimensionless parameter depending on the distribution of the weight of the links. Now what they observed, according to Barrett et al., the obtained network shows heavy tail distribution. So this is what? Heavy tail distribution. This is not a polynomial, this is not a Poisson. Then they plotted on a log scale. So this is a log scale, 10 power 01, 10 power 110, and 10 power 200. Here we can see 10 power 1 up to 10 power 8. So when they plotted this data on a log scale, again they also calculated the degree. So this inset shows degree, probability distribution of degree, okay, on log scale, the number of collaborators, and this is number of papers for particular scientists. So this vertical x-axis represent what? The scientist, and horizontal axis represent what? The number of papers. Similarly, when they analyze this air transportation network data, we can see when they plotted on log scale, we can see here that again this one is a heavy tail distribution, and when they found the slope, the decreasing curve of this particular distribution, again it was in the range of -2 to -3. So they declared that not only the degree, not only the fitness, but the strength of node is very important, and it's also the factor of scale-free phenomena in real-world networks. Now, due to scale-free topology, these networks become highly clustered, and average path length between nodes grows very slowly as the nodes increase in the networks. Further, scale-free networks become very robust and resilient under random attack, because if the network is random, it means the degree distribution of nodes is same. So they are very much robust under random attack. But the scale-free networks, again, they are very much robust under random attack, and they are very much fragile under target attack. Because if you will pinpoint the main nodes, if you block the main nodes, if you block the main links, then definitely it will collapse. So the table, this